Cylinder filling PSA, or pressure swing absorption plants, require a specialized piece of equipment to fill oxygen cylinders called a booster compressor. This critical component is both complex and unique to oxygen applications. Build Health International has drawn on our extensive experience to prepare and compile this series of videos. We will be reviewing some of the key considerations for maintaining and operating a booster compressor for PSA plant operators, technicians, and engineers. In this video series, we will be discussing booster compressor fundamentals, components, operations, planning maintenance, and performing maintenance. Reviewing each of these topics will help you prepare for the responsibilities of owning and maintaining your own booster compressor. In this video of the Booster Compressor Maintenance and Operation series, we will be reviewing the fundamentals of booster compressors.
Booster compressors are machines that increase the pressure of oxygen from an initial low pressure to a final higher pressure. There are two types of booster compressors commonly included in PSA plants: high pressure and low pressure boosters. High pressure boosters are essential for filling oxygen cylinders to the necessary high pressures. This is usually around 150 bar. Low pressure booster compressors compress to only 8 to 12 bar. They are used to send oxygen through piping systems at higher pressures than what a PSA plant could typically achieve. This video series will focus only on cylinder filling high pressure booster compressors. Within the PSA plant, the high pressure booster compressor is located after the oxygen storage tank and before the filling manifold. It is a key component of the oxygen delivery system as it compresses the medical grade oxygen produced by the PSA plant into the cylinders. A booster compressor must be present and working to fill cylinders. These cylinders are then transported to patients' bedsides to provide oxygen to patients in need. In order for a PSA plant to produce and deliver oxygen, the air compressor first takes in ambient air at 1 bar and compresses it to about 4 to 6 bar. This high pressure helps the oxygen generation process to be more efficient. However, it is still not high enough to fill cylinders effectively. This is where booster compressors come in. Booster compressors are designed to take in the 4 to 8 bar pressure produced by the PSA plant and compress it further to 120 to 150 bar. This high pressure allows more oxygen to be transported at one time. Compressing oxygen to 150 bar in a 50-liter cylinder allows users to transport 7,500 liters of oxygen in just a single cylinder. Smaller cylinders will contain less oxygen. This means they are faster to fill, but are more quickly depleted. The number of cylinders filled depends on both the PSA plant capacity and the booster compressor capacity. The limiting factor will always be the smaller of the two. There are two ways the booster compressor can be configured. First, the booster compressor is smaller than the PSA plant, meaning its capacity is less than the capacity of the PSA plant. In this case, the PSA plant has the ability to fill cylinders and send the remaining oxygen through pipelines to the bedsides. The second configuration is where the booster compressor is the same size or flow rate as the PSA plant. This configuration fills cylinders only. It is not recommended for a booster compressor to have more capacity than the PSA plant, as the larger size will be an unnecessary upfront cost and ongoing electrical load. Within these guidelines for all cases, the larger the booster compressor capacity, the more cylinders can be filled. When the plant has both cylinder filling and piping, the more cylinders filled, the less oxygen will be able to go through the pipelines. High-pressure booster compressors are often reciprocating compressors. Reciprocating compressors use pistons and do not use oil as a lubricant. The pistons are driven by a shaft inside each chamber to compress oxygen. The absence of oil in this process causes parts to wear out faster than in oil-lubricated systems, increasing the need for regular maintenance. Since many components require frequent replacement, it is important to account for these unique maintenance costs when budgeting for your booster compressor. The booster compressor must compress through multiple steps or stages in order to avoid excessive heat buildup, reduce mechanical stress, and achieve high final pressures efficiently and safely. Each stage works the same way. The oxygen flows through each stage sequentially, increasing pressure incrementally. Each stage can be monitored by their designated pressure gauge. As shown in the example table, oxygen flows through each of the 4 stages sequentially, doubling or even tripling the pressure each stage, until it reaches the target output pressure at the final discharge point. Typically, the larger the capacity of the booster compressor, the greater number of stages it will have. The photos on the slide show two different sized Bylon booster compressors, the GOW80 and the GOW3. The GOW80 has 6 stages and a flow rate of 80 cubic meters per hour, while the GOW3 has 2 stages and a flow rate of only 3 cubic meters per hour. The difference in capacity can be seen by their size and number of stages. The GOW3 has only 3 pressure gauges, while the GOW80 has 7. Each booster has 1 more gauge than their total number of stages. Both of these booster compressors output oxygen at 120 to 200 bar, but due to the lower flow rate, the GOW3 is able to achieve that pressure in only 2 stages, as opposed to the GOW80, which takes 6 stages. Many different manufacturers and models of booster compressors exist. This slide shows examples of 4 boosters from different manufacturers of different capacities, and all with varying number of stages. Each model is different, but all follow the same working principles. Choosing the right one for your plant depends on capacity, price, availability, and service requirements. High-pressure booster compressors are essential for supplying life-saving oxygen to patients' bedsides. Booster compressors are required for filling oxygen cylinders. The booster compressor's oil-free design makes them safe in oxygen-rich environments, but requires frequent maintenance. With proper upkeep, booster compressors ensure a reliable and uninterrupted supply of oxygen when it is needed most.
We hope that you have enjoyed the introduction to booster compressors. Continue on to learn more about booster compressor components.